This part will thread into the other end of the nut. Let's see how it all goes together. Again, a PVC end cap is used, a hole having been drilled in the center to allow the barrel extension to pass through. Note that this cap is threaded, as is the PVC suppressor body that will be used. A washer distributes the force of screwing down the assembly over the PVC cap. The barrel extension and outside threaded connector are passed through, and then the nut is screwed down, locking the PVC cap between the barrel extension on either side. This ensures correct and repeatable alignment. The rubber material of the bicycle clamp provides an excellent gas seal, and the clamp itself, when screwed down, provides a very strong attachment. Using various size plumbing fixtures and sometimes brass bushings, we found this method of attachment suitable for a wide variety of weapons. Threaded barreled weapons provide another alternative for suppressor attachment. Some weapons, such as this AR-15 rifle, come equipped with flash suppressors. After loosening with a wrench, the flash suppressor can be removed, exposing the threaded barrel. Gun steel, such as used in barrels of rifles and pistols, is generally too hard to cut with hand taps or dies. However, the soft brass bushing in this PVC end cap assembly was hand tapped using a common hardware store tap to match the AR-15 threads. The device you see here was not designed as a noise suppressor, but as a test chamber to allow daylight videography of muzzle flash, as we will see later. For weapons using removable barrels, such as the 9mm Sten gun, threaded barrels are available through mail order. This device is for the Colt Woodsman and requires gunsmithing to install. By far, the most satisfactory improvised method for attaching suppressors is the mail-order muzzle adapter. These adapters provide the benefits of a threaded barrel, perfect alignment, and repeatability, without any modifications to the weapon. Like the early Maxim couplings, each muzzle adapter is made for a specific weapon. This one is for the Ruger Mark II pistol. The machined unit is simply slipped over the front sight and then secured by tightening the locking clamps. This method allows all the benefits of a threaded barrel without any modifications to the firearm. We now examine just how a suppressor works. First, we can identify three sources of firearm noise. The first of these is simple mechanical noise. Mechanical noise is simply the noise of the moving parts slamming into one another. Revolvers cannot be effectively suppressed because so much of the hot gases escape between the cylinder and barrel gap. Suppressors have no effect on a firearm's mechanical noise. Muzzle blast is the second and most significant source of firearm noise. The hot expanding gases of the burning propellant drive the bullet down the barrel. When we hear a gunshot, we are primarily hearing these hot gases heating the cooler outside air as they exit the muzzle. A third source of firearm noise is supersonic crack. A bullet moving faster than the speed of sound creates a mini-sonic boom, similar to a jet aircraft. To avoid supersonic crack, the bullet's velocity must be reduced to less than the speed of sound. There are only two ways to achieve this. One is to reduce the powder charge. This reduces the velocity of the bullet, but in some weapons the reduced powder charge does not cycle the action reliably. The second method of achieving subsonic bullet velocity is to port or drill holes in the barrel to reduce its efficiency. The hot gases escaping from these holes will be trapped by the suppressor body, which slips over the barrel. Porting a barrel requires machine tools to be done properly. An ordinary hand drill would destroy the weapon's accuracy. Let's examine another relevant effect of a bullet moving faster than the speed of sound. This graph shows how a bullet loses velocity, measured in feet per second on the vertical scale, as it moves downrange, measured in hundreds of yards on the scale at bottom. The flat blue line represents the constant speed of sound at just below 1,000 feet per second. Note that at about 600 yards the graphs intersect, and the bullet is now subsonic. Observe that after the bullet has gone downrange 250 yards, its initial velocity of 3,300 feet per second has dropped to about 2,000 feet per second, about twice the speed of sound. The velocity of the bullet continues to drop till at 600 yards, its speed is below 1,000 feet per second, roughly equal to the speed of sound. From this point on, the bullet is not moving supersonically, therefore no sonic crack will be heard. But at such a distance, the sound of the shot, its decibel level, has dropped dramatically as well. We conducted these field experiments to demonstrate these effects. Notice that the only sound recorded is the impact of the bullet itself, not the sound of the shot. After traveling 570 yards, the bullet is moving at subsonic velocity, so there's no supersonic crack. The camera does not record the sound of the shot at this distance. Let's watch again. The drop in decibel level and the loss of velocity, which occur at long range, almost amount to a natural suppressor effect. This is why military snipers most often do not use suppressors when firing at great range. Since a silencer or suppressor only affects muzzle blast, let's examine this phenomenon more closely. The hot gases of muzzle blast result from the burning of the powder, a chemical propellant in the cartridge. Consequently, the amount of muzzle blast is directly proportional to the size of the cartridge being fired. Bigger cartridges need more propellant and thus create more muzzle blast and noise. At far right is a high-powered rifle cartridge and its powder charge. At far left are 22 rimfire cartridges and their powder charge. In this next experiment, the device was constructed to allow videography of the muzzle blast of this AR-15 rifle. Observe. The prime function of a suppressor is to cool and reduce the velocity of these hot expanding gases. Let's now examine how this is accomplished. A perforated barrel extension, which can be simply rolled up screen, allows the hot gases to escape into the baffling material. Often, this material is steel wool. This cools the gases as they transfer heat to the steel wool. Next, baffles strip more of the hot gases from the bullet. The spaces between the baffles allow the gas to further expand and thus cool. A rubber wipe completes the job of retarding the hot gases from freely exiting the muzzle as the bullet exits. The following computer animation depicts this process more dynamically. Suppressor designs vary somewhat, but this one is typical. The hot gases first hit a large volume chamber, allowing them to expand. When a gas expands, its pressure drops, as does its temperature. Steel wool or copper scouring pads are often used in this chamber. Sometimes lithium or white grease is added to the steel wool to further cool and dampen the gas.